Hi everyone, Mr. Ford here. I just wanted to walk through a sample problem for you to assist with the projectile motion lab for your angled shot. This is within your packet. It's projectile motion uh, worksheet 4, number 1. So it's a very similar scenario where the ball is going to be launched off this ramp. So the ball is really going to be here, moving at that initial velocity of 1.5 meters per second. And I am going to redraw this down below, but I just want to give you guys an idea. And we know the height from the ground, and we just need to know where it's going to land, what the delta x is going to be. So when solving any of these types of problems, we want to separate the main workload into, let's go green. Whatever's happening in the x direction and whatever's happening in the y direction. Keeping in mind, anything in the x direction is going to be constant, so our Vx is constant, but it's not going to be that 1.5, because that 1.5 meters per second is both moving vertically and horizontally at the same time. So we'll address that in a moment. And to find the displacement in the x direction, we used our constant velocity in the x direction times the time it had to move or fall for, really, where time was that common variable, both x and y. It was like that roommate that talks to everybody, for the roommates that don't talk. In the y direction, we do have acceleration because gravity is acting downward on the ball at all times, whether it's on its way up or on its way down. So we will have an initial velocity in the y direction, and of course a final velocity in the y direction, but we're not concerned with that as of yet. Just take note, range is another way of saying horizontal displacement of the projectile. So let's kind of break off for a second. So we have this 1.5 meters per second at an angle of 20 degrees. So this is where that vectors unit comes into play. So that 1.5, at the moment that it's leaving the table or the ramp or the launcher, whatever the scenario is, it's going to have a horizontal component, which is going to be constant. So the whole time that ball is moving, whatever its horizontal component is constant. Its vertical constant, or sorry, that's not very vertical. Vertical component is not going to be constant. So we're only going to look at its initial velocity for right now, for what this question is asking us. So it's its initial y component. So the way this problem is set up, we know how to get our answer here. There's an easy way to calculate Vx, and then time we're going to get from the y. So just breaking up this 1.5 into components to get Vx. Okay, I didn't label my angle. So to get my horizontal side, I'm going to use cosine. So cosine of 20 degrees is adjacent, which is my x component of velocity, over the hypotenuse, where if I plug that in, I get 1.41 meters per second, and that's positive. To get my other component, sine 20, is going to be my VIY. Sorry, I should have color coded this better. And that's going to be this. So I need to make sure that I use these velocities in the appropriate spots. So to get delta x, which is my final answer to the problem, I already have the Vx, like I mentioned, and I'm just looking for my horizontal information as far as time goes. So that I'm going to look for over here because it's going to be the same. So I have my VIY that I calculated. I know my delta y was my 1.2 meters negative because we're starting, when we look right here, we're starting up at some position and we're ending down on the ground. So the net or overall displacement, like a snapshot, is going to be downward. So right now, we don't have the time. We're looking for the time. So our equation, of course, has to have time in it. We don't know the final velocity at this point. So our formula to use cannot have that in as well. So the only option for that is this equation, which we know all of these variables. We know VIY, we know delta y, and we know a, and then we just have t left over. So this is that scenario where we have two t's, and some of you may recognize this as a quadratic equation. So you're going to have to either use the solver that's in your calculator if you have that programmed, graph it. Just Google a quadratic equation calculator. I wouldn't go through and plug in all of the numbers in the real quadratic formula. It's a lot of button pushing and easy to make a mistake. So if you have the resources available to you, use some other way. So that will get you your t, which you then can bring back over here, and that will give you your answer as far as where this is going to land. Now, this is just a model. It's not exactly what's going on in our lab. There's another little nuance that some groups have already figured out, some groups have not. But if you are successful in your horizontal launch, then you probably know what I'm talking about. So I'll walk through this a little bit more in detail or answer questions for your lab when you have them. So hopefully that helped.